This is lesson 2.1 on ratios and proportions. So the first part is to go ahead and do the warm-up. So with the warm-up, the goal is to go ahead and draw this figure, but to double its size. So go ahead and pause the video, draw the figure, and then unpause it. And then we're going to ask some questions. Double this, I'm going to first start by just measuring this length here, which looks to be about 4.1, between 4.1 and 4.2. So I'm actually going to draw it on the same figure, so I'm just going to take this line and try and just double its length. Then I'm just going to measure another between 4.1 and 4.2. So somewhere about here, I'll put a dot, and then I'll erase the extended line that I made. So essentially I doubled this length. I'm going to do the same thing on the bottom here. So I'm just going to try and trace this line and just make double its length. I obviously overdrew it, but I could erase what's ever extra. This looks like about 5.7, so I'll come over here and double its length, 5.7, which is about here. There we go. Now, here's the problem. I doubled this length, but I didn't double these. That's not going to work. I'm going to have to erase that. I think I'm going to have to double this length here before I can do that. So we will go ahead and extend this line. And this isn't the only right way to do it. So there's more than one way to make this happen. That looks like almost 3.2, so I'm going to go ahead and mark it about between 3.1 and 3.2, right about there. There we go. And now this is where it gets a little bit more challenging. I want to draw a line that's horizontal. How do I ensure that that's the case? Well, I'm going to go ahead and use a method here to try and get this measurement. So we said this was 5.7, right, this distance. So I need this to be about, so 5.7, if I double that, that's 11.4 if I double it. So I'm going to go ahead and draw out here. I'm going to mark about 11.4, which is somewhere about here, right? That's a rough guess. Now, I'm going to measure this one. That is about 3.1. If I double that, that's 6.2. So if I come out here and do 6.2, that actually matches this dot right here. So that dot was actually a pretty good guess. This isn't going to be perfect, but it should be a pretty good guess of a doubled figure here. Now, if I truly doubled this figure, the question is, what is true about the angles? So in other words, how do the angles compare from this figure to the larger figure? So go and just think about what do you think might be true about that? Are they the same? Are they different sizes? I doubled the figure. Did it change the angle sizes? Well, this angle is shared by both figures, the original and the enlarged one. So clearly this is the same. These angles should be the same. This angle and this angle should be the same. This angle and this angle should be the same. So the angles should be the same size. I'm going to put corresponding. The corresponding angles should be the same size. right? So this angle is obviously equal to itself. These two angles should be the same. These two angles should be the same. And these two angles should be the same. When I say corresponding, I mean they are in the same position as the original, right? This was the top right angle of the original figure. That's the top right of the doubled figure. So the angles are the same. So what is true about the sides? Well, we doubled them, right? They told us to double the figure, and we understood that to mean that we're doubling the side lengths. So the lengths are double. All right. Now we're going to talk about ratios. A ratio is a comparison of two or more numbers, and it indicates the numbers' sizes in relation to each other. So if I say 1/2, that is the same as a 1:2 ratio. Another simple way to describe another way to describe a ratio is simply a fraction. It could be written as a fraction, but it could also be written in this form. So 2/3 could be 2 to 3, right? So, or 2 out of 3. Now, a proportion is an equation in which two ratios are set equal to each other. So, for this, I could say 1/2 equals 4/8. This is a proportion, and it is a true statement. So we know that 1/2 as a decimal, if I change it to a decimal form, 1 divided by 2, no, that's times. 1 divided by 2 is 0.5. 4 divided by 8, also 0.5. These are equivalent. If you think about them as pies, if I had a pie, and I had half a pie, so 1 out of 2 pieces, if I did a second pie, and I cut it into 8 pieces, and I have 4 of those, so I'll shade 4 of those 8 pieces, we can see that's the same amount of pie. So 4 out of 8 and 1 out of 2, that's the same amount of pie. It represents the same amount. It's just how many pieces make up a whole changes. But this is still an equivalent amount. It's half a pie in each case. So in class, what we wound up doing, there was an activity, and we measured everyone's heights, and then we measured their wingspan, which was from the tip of their left hand to the tip of their right hand with their arms spread open, right? So what we're doing is, if I have a person here, right, we're measuring the wingspan, and then we're measuring their height. And then we're gonna, so we did this with everyone that was here in class, and what we found out is that these numbers were very close. It was almost a 1-to-1 ratio. So typically, the wingspan of a person is pretty close, or if not equal to their height. And so that was the whole point of it, is to look at it, and then we took those values. So I'll just give you one example. So my wingspan was 70 inches, and my height was 70 5/8 inches for height. So to look at the ratio, and I could do wingspan to height or height to wingspan. So I do believe we did 70 over 70 5/8 to make it into a fraction. And then we change that to a decimal to get a value. And so if we get a value close to 1, that means it's very close to a 1-to-1 ratio. Now 5/8, I had to change that. I had to change that into a decimal. So it was 70 over 70.625. So 70 divided by 70.625. And that gave me a 0.9911 value. So that's very close to 1. So that shows us that it is very close to a 1-to-1 ratio. And we just confirmed that with everyone in class. Alright. So next thing we took a look at these two rectangles. And we wanted to compare the lengths and the widths and make a conjecture about the ratios. So I'm going to go and quickly just do measurements here for those. You can do the same with the ruler. We're going to do this in centimeters. And I'll just pause it so you don't have to watch me do the measurements, and then we'll use the data. And measurements, these ones on the smaller one didn't turn out like perfectly. They weren't like real close to the line, so I had to put 3.25 and 5.45. And then here, these did work out a little bit nicer, 4.9 and 8.2. Now, what we want to do is compare the short sides together and the long sides together in a ratio. So I'm going to take the 3.25 and divide it by 4.9, and we're going to change that to a decimal value to see how close, or see what that value becomes. So 3.25, sorry, I just have this blind spot over here. I get the shadow, you can't see the calculator. I move it to the other side. 4.9, that's about 0.66. So 0.66 for that one. Now if we do the other two, the 5.45 over the 8.2, so these are the long sides of the rectangles, we're going to do the similar thing, 5.45 divided by 8.2, and look, we get about 0.66. So that value, 0.66, that's real close to 0.6 repeating. That's real close to the fraction 2/3. So we can see that is pretty consistent. So we could almost say that this rectangle is about 66% of the size of the big one. So this is about 66% of that size. What would happen if I flipped this? What if I did 4.9 divided by 3.25, and I put the big number 8.2 over 5.45. So instead of having the small numbers on top and the big numbers on the bottom, we're going to flip them. So 4.9 divided by 3.25 gives me about 1.5. About 1.5. I'm just going to go one decimal on that. And if I do the 8.2 divided by the 5.45, I get 1.5 again. So we could say that the big rectangle is about 1.5 times bigger than the small one. So when we get these ratios, depending on whether you put the big number or the small number on top, if you put the small number on top, it'll kind of tell you how much or what part of the big figure the small one is. And if you do it the other way with the big number on top, it'll show you how many times bigger the large object is from the small. Well, let's consider these two rectangles. With these two rectangles, if they're proportional, could we make a guess on the length of this side? Now let's compare these two. I'm going to do the same thing. I'm going to take the ratio of the small sides. I'm going to put 2/6 or 6 over 2. We can look at both of these. 2/6 reduces to 1/3, or 0.3 repeating. 6 over 2 is just 3. Well, I think we can say then that this side is 3 times bigger than that side, right? The corresponding side on the small rectangle. So should that be true about the long side of the rectangle? If this is 10, what should this length be? Well, it should be 30. Now that's one way to do this. You could look at kind of the ratio that's happening. Get a ratio or an idea of the size change, like this number. Get that ratio for that comparison. But you could also use a proportion to do this. Now a proportion, once again, is equal fractions. So I could take like the values from the small side, which is 2 and 6, and then I could do the long side and get those values. Well, for this triangle, or for this rectangle, it's 10. For the other one, this is our unknown. We'll mark that as an X. Now I want to point out both these numbers represented the small side, and both these numbers represented the long side. On the top, we represented the small rectangle, and on the bottom we did the big rectangle. This is important to note because when you set up a proportion, it should make sense that the things that are on the top or on the bottom should be the same type of thing. In this case, these were sides of the small rectangle, these were sides of the big rectangle. When you're looking vertically, they should also correspond. These both were the small sides of the rectangles, and these were the long sides of the rectangles. So that should work. Now to solve this, I'm going to go and just bring this up here. There's a couple ways to do this, but what I really need to do is get x by itself in the numerator. And one way we can do that is to multiply both sides by the denominator of x. So we're going to multiply the top, both sides to x. Now this is going to cancel this x. We learned this in Algebra 1 when we were doing solving equations, so if you took Algebra 1 with me, to clear a fraction, to get rid of a denominator, you multiply by that denominator. Since this is 10 divided by x, multiplying by x cancels it. So it's just gone and you're just left with 10. On this side then I have 2x over 6. Well, how do I clear this fraction? Once again, multiply by the denominator. So multiply both sides by 6. Those cancel and I'm left with 2x equals 60. Last step, divide both sides by 2. X equals 30, and that is the answer that we already got using the other method. Now, we are going to continue to use proportions quite a bit in this unit. In fact, a lot of the math we're going to be using involves proportions. So we'll continue to use them for the remaining problems. The next problem. We have a map that is scaled 1 inch equals 5 miles, and the distance between 2 points on the map is 3 inches. So how far are those points in real life? So go ahead and pause, see if you can figure out the answer, and then we'll see if you got it right. Okay, so hopefully you went through and tried to figure out what the answer is. If you got 15 miles, you would be correct. If 1 inch is 5 miles, well then 3 inches would be 3 things of 5 miles, right, which would be 15. But we're going to set up a proportion to solve that, because not all the problems are going to be ones that you can just look at and do in your head. This one, a lot of people can, but setting up the proportion is going to be important. So 1 inch is 5 miles. That's what it tells us here. And I'm putting in the units because the units are going to help us determine whether we set it up right. The units should always either match horizontally or vertically, but never diagonally. So since this is 1 inch is 5 miles, this 3 inches has to go here. It has to go across from the 1 inch. It cannot go here. So that's really important. This is our unknown. We don't know how many miles they are in real life. That's what we're trying to find. Now I'm going to show you a trick. Now in the first example I had you multiply both sides to x to clear this, but something you can do with proportions is you can flip both sides. So I flipped the 1/5 to make it 5 over 1 and the 3 over x to x over 3. But you have to do both of them. You can't just flip one side. So you can flip the fractions on both sides. Now, in order to solve for x, all you need to do is clear this fraction. Just get rid of the 3. So we'll multiply both sides by 3. Please notice I'm putting them up here I am not putting them here. A lot of times I have people will do this. They'll put times 3. You do not put that on the bottom. When you multiply to both sides, you multiply to the numerators. You do not multiply to the denominators. Now, the 3's cancel each other, and you're left with x, and 3 times 5 is 15, and that is the answer we said it would be, 15 miles. Alright. I know this video's gone for about 20 minutes, so I'm going to go ahead and pause it here and make this, or end it here. This is going to be part 1, so please continue on to part 2.